At this point, you should be familiar with drawing chairs and recognizing which substituents are axial or equatorial. An important rule for drawing rings is that larger substituents are always going to be more stable in an equatorial position. I'll talk about why in a minute. Cyclohexane chairs are going to flip so that they can orient substituents equatorially. So if we have this 1-methyl cyclohexane, let's go ahead and draw it out. You can draw either chair conformation that you feel comfortable with to start, and you can pick any carbon because there's only one substituent. So I'm going to pick this bottom left one because I like drawing axial groups. I think it's a little bit easier. If drawn like this, it's drawn correctly. This dashed line means that the methyl group is down, and that's how it's oriented in this case. As I said before, substituents are more stable in an equatorial position. So what will happen is we will have a ring flip where after the flip, the downward axial methyl group will now be shifted here to a downward equatorial methyl group. This conformation will be more stable. Why is it more stable? Well, let's draw in some other axial hydrogens on the example on the left. There's a hydrogen here, and there's also a hydrogen here. Notice these are occupying, if we draw in all of the hydrogen atoms on this methyl group, they're occupying similar spaces. This is called diaxial strain. It's strain between two axial atoms, and there are two sources of that strain in this conformation. If we take a look at our equatorial substituent, we can draw in the axial hydrogens, but they're pointed away. They're pointing in a different direction. They're straight down rather than to the side. If we draw the equatorial hydrogens, notice they're not pointed in the same direction as this methyl group either. So by orienting this methyl group in an equatorial position, we are isolating it and we're giving it more room so that there's not as much steric or size crowding. Let's take another example with two substituents. In this case, we've got 1-ethyl, doing alphabetically, 2-methyl cyclohexane. In this case, these are going in opposite directions. So we'll call this type of substitution trans. Trans means opposite. Let's go ahead and draw these before we think about any of the rules. Draw a chair. The 1 position is the ethyl group. So I'm going to draw that up axially. I don't have to draw both carbons of the ethyl group. I can write ET. Now we could go either way. We can go left or right. For the methyl group, I'm going to go to down and to the right. This methyl group is pointed down. That's what the dashes mean. So the methyl group goes down here. In this case, we have two substituents, and they're both in axial positions. So they're both going to experience strain as they clash with the hydrogens. So there's some strain here and here, and also some strain between these hydrogens and this methyl group. So what's going to happen is this cyclohexane will undergo a flip so that the axial substituents will be oriented equatorially. So if this was carbon 1 originally, remember that when we do a chair flip, we're going to shift the position of the carbon. So instead of being at the top right, we'll make it at the bottom right. It's still going to be oriented upward. The ethyl group will be equatorial now. We will shift the methyl group as well. It's still going to be down, but in this case, it's going to be oriented equatorially. So for trans cyclohexane in this case, this will be the more stable conformation. Let's do one more example. In this case, we have cis cyclohexane. Cis means these bonds are oriented in the same direction. Let's draw our chair. Again, we're going to put the ethyl group here on the top. It's axial. Now, the methyl group is pointed up as well. That's what the wedge means. So if we drew it axially like this, that's the hydrogen group. That's pointed down. The methyl group is equatorial here. So if we compare the strain, there's no strain associated with the equatorial methyl, but the ethyl group is going to experience strain with these two hydrogen atoms. Ethyl groups are larger than methyl groups, so this is going to force a chair flip so that the ethyl group will be equatorial instead. Let's draw our flipped chair. And again, just like before, the ethyl group is going to shift down one. We're going to draw this equatorially and up. If you ever want to check yourself, just draw on the hydrogen. That's clearly pointing down. The methyl group here, which was equatorial, is now going to be axial and pointed up. So now in this case, we have one equatorial group and one axial group, but the equatorial group is larger. So between these two conformations, this will be more stable.